So the first thing we need to do is actually talk about energy itself and kind of take a step back and define what energy is, right? So energy is basically the capacity to do work or to produce heat. So again, it's the capacity to do work, and notice the terminology you're saying do work, and when you say do work, we're going to talk about this, but we're talking about doing work on a system. Okay, so it's the capacity to do work or to produce heat, and we'll talk about how to calculate that production of heat, and that's actually what we call enthalpy, but we'll get to that. Okay, so recall that the law of conservation of energy states that you can't create or destroy energy, right? That's one of the fundamental laws of chemistry and even physics. It's that you cannot convert energy from one form to another. You can convert energy from one form to another, but you can't destroy it or you can't create it, okay? So that's the law of conservation of energy. All right, so law conservation of energy. Right. So again, potential energy then is the energy that's dependent on the position or the composition of whatever you're dealing with, right? So if the classic example is the rock on top of the hill, that has potential energy because it has it's going to gain energy as it moves down. Its position energy, it's based on its position in that sense. It can also be based on a composition, right? So that's potential energy. Now, kinetic energy, on the other hand, so potential energy we're going to call PE. Kinetic energy is the energy of motion, right? It's the energy due to motion of the object, and it's very dependent on the mass of the object, right? It's dependent on the mass of the object and then how fast that object's been moving. So the classic equation for the kinetic energy is 1/2 mv squared, and this makes sense because it's dependent on the mass and the speed at which that object is moving. So the ball rolling down the hill has a certain mass because the ball itself has a mass, and moving down a hill has some sort of velocity, has a direction and speed, so it has some sort of velocity, right? So again, we said energy can be converted from one form to another, but it can't be created or destroyed. So that's one of the key points. So the other thing you need to understand is what is the difference between heat and temperature. Okay, so heat versus temperature. Right? Temperature, remember, is the property that reflects just basically random motion of any particle that we're talking about in any substance. So it's the random motion. It's a description of the random motion. Okay, heat though, it's different from temperature, and I think this is one of those concepts that students always mix up. Temperature and heat are different things. Heat involves the actual transfer of energy. It involves the transfer of energy from one object to another, because of a temperature difference. So again, it's the transfer of energy between two products or between two substances, and it's due to a temperature difference, a change in temperature. I'm just going to say delta T, right? Again, delta represents change in. That should be pretty obvious by now. Okay. So heat is not a substance that's kind of contained by an object. Okay, so that's very, very, you have to understand that. Heat is the transfer of energy. It's not something that a substance can contain. Okay, so make sure you understand the distinction between the two. Okay, now if we go from an initial arrangement to a final arrangement in any change of a system, we have to talk about the work. We have to talk about the work that's done on the system. Okay, so work. We have to define work now. So work is basically is the force that's going to act over a distance. The force that acts over a distance. Okay. For example, if you want to take a ball that's at height h and you want to lift it up to height hf or final. this is H initial. If we want to take that ball and lift it in the air, we have to exert some sort of force over this distance, right? And that is work, to raise that ball from its original position to its final one, right? Now, and even in talking about this itself will have a potential energy and a kinetic energy. As we move it, it's going to have kinetic energy, but as it's laying on the ground, it's going to have potential energy. And in this sense, potential energy will be negative because we're actually putting energy in to lift it up, right? So we have to describe the transfer energy in two ways, right? Because this is both talking about energy. So the first way we're going to describe energy, transfer of energy, is through work, and then the second one was heat. Okay? We said again, heat was the transfer of energy dependent on the change of because there's a change in temperature. So we can talk about transfer of energy by work and heat. All right, so that's how we're going to describe a transfer in energy. Now, energy can the transfer of energy, basically we can divide that between work and heat, and it's dependent on specific conditions. So which of these are going to be more effective for that transfer of energy is dependent on certain specific conditions, okay? And that condition is the pathway. So the pathway that, anything for, let's just take for example a ball rolling down a hill. So there's a hill, a ball that rolls down. There's a pathway that this ball is going to take. How much work or heat is done is dependent on that pathway. Okay, so let's take an example of this. So if there's a surface of the hill, right? This hill that we're talking about, the surface of the hill could be rough, right? So if we talk about if it's rough, then you're actually producing friction. So okay, and that friction is heating up the ball. That's a type of transfer of energy. Now, and that's frictional heating, right? And if it moves slowly, if it moves faster, so that's all dependent on the amount of kinetic energy that's going to be put into the system, right? And so regardless of the condition of the pathway that we're taking, the total energy that's going to be transferred is going to be constant, regardless of what we're talking about, okay? The thing that changes is that the amounts of heat in the work are going to differ. The total energy will be constant, so total energy is going to be constant, but the amounts that are going to differ are going to be the heat and the work. So heat and or work will differ, meaning they're not constant. They can and will change. Okay, so that's key. Then energy that changes in the entire system is independent of the pathway. Okay, so this thing right here, this change, when you call total energy, it's also a change in energy, right? And so the total energy or the change in energy is independent of the pathway, but heat and work are dependent on the pathway because they will differ. So they are dependent on the pathway. So that brings us to another concept that's called state function or state property. And all of this kind of will make sense on why we're talking about this in the thermodynamic lecture. I know it's a bit of a physics topic, but it will make sense on why this is important. So state function or state property, right? So state function, right, is basically the property of the system, right? Again, it's the system that's only dependent on the present state, meaning whatever is the status quo, the instantaneous point in time of that system, that is its state function. The status of that system in that moment in time, that is the state function. So this is dependent only on present state, dependent only on present state. Okay, so that state function or state property is not dependent in any way of what happened in the past or the future. Okay, that is a state function, right? So meaning, in other words, the value of that state function is not going to be dependent on how the system is going to get to that present state. It's irrelevant of how the system got to that present state. What matters is that you are in that present state, and that's what the state function is dependent on. So that kind of leads us to a very important characteristic of state function, okay? And that is that a change in the function is going from one state to another state is independent, right, of of the pathway that you're taking. So let's take an example here, right? So if we're on point A right here, and we're trying to get to point B, right? And there's many different pathways I can take. I can take a easy straight shot, straight pathway. I can, make it a little bit harder, or because I'm feeling very crazy today, I can just go nuts. Irrelevant of what path I take, if I take path 1, 2, or 3, it doesn't matter, right? And that's very important for a state function. What really matters for a state function is that present time. The point A or the point B is that instantaneous value. It's not the change that matters. It's not how you got there that matters, right? So then the next logical step is to talk about, well, given all this work and heat, that the fact that, so if we're saying that that work and heat are going to depend on the pathway that's taken, that means that work and heat are not state functions, right? In that sense, then total energy is a state function. So this is a state function. And the heat and work then are not state functions, because they are not, because they do depend on the pathway that's taken, not state functions. Okay, so let's kind of bring this back to a more chemical sense, right? So let's talk about the combustion of methane, and we'll introduce some new terms and for all this to make sense here. So talk about the combustion of methane. So that's methane is just CH4. Again, this is the gaseous state. We're going to add O2. Again, this is gaseous, and any combustion reaction, we're always going to form CO2 plus H2O, gas, and this is gas, and then just balance it out. Okay, and this should be 2. All right. So what you're getting here is actually we're going to get a release of energy, right? We're going to get a release of energy. So energy in this situation is going to be our product, because we're getting a release of energy. And so we can call that. So another way we can look at this is if I take 2 beakers, and I know you can't put methane in a beaker, but if I take just drop some molecules of methane and some oxygen, put that in green, we're going to form carbon dioxide and let's say water in blue, water, right? And this is in gaseous state. So what's going on here? And the key point here is that we're releasing energy, that energy is being removed from the system. So energy is released, right? This has nothing to do with anything besides the fact that it's releasing energy. Okay, so we kind of need to discuss this. We kind of need to take our universe and divide it into 2 parts. Okay, so we're going to divide it into the system versus the surrounding. Okay, so the system is the part of the universe which we want to focus our attention to. So our attention. And the surroundings is everything else. Okay, now in this case, what we're going to do is we're going to define the system as the reactants and the products. So right, so this, whatever's happening here is part of our system, and then the surroundings are basically whatever this reaction is taking place in. So if it was a furnace, that's a good example of where methane is taking place. A furnace, that would be our surroundings, or anything else that's in relation to those reactants and products. Okay, so when we have the reaction that kind of evolves heat, like in this case, we're going to call that an exothermic reaction. So when we release heat, right, when we release heat from a system, we're going to call that a exothermic reaction. And again, exo means, right, exo means out of. Right, so we're going to release heat. That means that energy is flowing out of the system. So when we say release heat, remember heat was a transfer of energy. So what we're saying here is that energy is flowing out of the system. Okay, the energy is flowing out of the system. So in our example here, the combustion of methane, we're going to take energy and it's going to flow out of the system as heat. And that's key. It's going to flow out as heat. Right? Now, reactions that are going to absorb energy, right? They're going to be called opposite of that. So they're the endothermic reactions. So reactions that absorb heat or energy, right, are going to be called endothermic. Endothermic. So, meaning, another way we can say this is that heat is flowing into the system. Heat is flowing into the system. Right? So then, let's talk about an example of that. So we talk about the formation of nitric oxide, right, from nitrogen and oxygen. So it's just N2 gas plus O2 gas plus energy in the form of heat is going to yield 2NO, or just nitric oxide, right? And so we're putting in heat to form this product, okay? So where exactly is this energy that's released as heat, or a heat when it's released as heat in an exothermic reaction, or when it's absorbed as heat in an endothermic? Where's this energy coming from, right? The answer is basically in the difference in the potential energies between the products and the reactants. That's where the energy is coming from. It's the difference in the potential energies. So whichever one has a lower potential energy will kind of determine where the heat will flow. Okay, so we know that the total energy is conserved, right? We said we can't create or destroy energy, so the total energy is going to be conserved from the systems into the surroundings, regardless of if it's an endothermic or an exothermic reaction. But if we talk about specifically an exothermic reaction, it means that the energy is going to be gained by this by the surroundings. It has to be equal to the energy that's lost by the system. So exothermic, when we say that the energy lost by the system is equal to the energy that's gained by the surroundings, right? That is the only way we can conserve our energy. So in the combustion of methane, when we talked about it before, the energy content of the system was decreasing because we're releasing heat. But that means that heat has to go somewhere, so it's going to our surroundings, right? And when we say the energy content is decreasing, what it means is that 1 mole of the carbon dioxide and 2 moles of the water molecules possess less potential energy than the reactants of 1 mole of methane and the 2 moles of oxygen, right? So let's just scrolling back up here. These guys have less potential energy than these. So this has more potential energy. In other words, PE final is less than PE initial. Okay? The heat flowing into the surroundings is going to result, which is what's happening here, the heat that's flowing into the surroundings or out of the system is causing a lowering of the potential energy of the reaction system. Okay? This is something that's always going to hold true. So in an exothermic reaction, the potential energy of the products is always going to be lower than the potential energy of the reactants. So in any exothermic reaction, some of the potential energy that's stored in the chemical bonds, right, in these chemical bonds, is being converted to thermal energy, and then kinetic energy, which is basically another form of thermal energy, via heat. That is how it's doing that. Potential energy is being converted to thermal energy, and that's why the potential energy of the products is going to be less. And that's in an exothermic reaction, because energy will be released to the surroundings. Okay? So that brings us to the talk of endothermic reaction, so potential energy and endothermic reaction. So the opposite's true, right? And the opposite has to be true. If we're absorbing heat from the surroundings, right? If we're absorbing heat from the surroundings like we did with the formation of nitric oxide, if we're absorbing heat, that means we're taking heat away from the surroundings. So this is endothermic. So in an endothermic reaction, the energy that's gained by the system is equal to the energy lost by the surroundings, right? And in this case, we're putting in the potential energy is going to be higher in the reactants than in the products, because now you're putting in that thermal energy. That thermal energy gets converted to potential energy. Now the products are going to have a higher potential energy. Okay, so the study of energy and its interconversions, right, is what we call thermodynamics, and that's why this is an entire field on thermodynamics. So the law of conservation of energy, where we say we can't create or energy or destroy energy, it's also called the first law of thermodynamics. Okay, it is basically saying that the energy of the universe is constant. It does not change. It changes form, but it does not change. That is the first law of thermodynamics. That brings us to a very important topic of internal energy. So what is internal energy? Now, we've been talking about heat and work, but the one big problem is, well, how can we actually calculate the amount of heat that system is using, right? And we have this method of saying, hey, this is how much heat or work is being done. It's dependent on the pathway, but how much actual heat is that system using, right? So internal energy it could be described basically as the sum of the kinetic and the potential energies, right? So Ke plus Pe, and this is more of a physical sense, more physical physics sense, right? It's the sum of the kinetic and the potential energies of all the particles in the system, right? So if we talk about in terms of chemistry, or in terms of a more thermodynamic concept, then the internal energy of a system can be changed by a flow of work, heat, or both. Because remember what we said, that work and heat were both dependent on the kinetic and the potential energies. So that's another way we can say it, is that the internal energy of a system can be changed by a flow of work, heat, or both, right? So in terms of an equation, it's basically delta E, right? In physics, they use U, so don't get that confused. But delta E is equal to Q, which is heat, plus W, which is work. Now, the sign is very, very important here, okay? So again, so delta E represents the change in internal energy, Q represents heat, and W is work. The positive sign here is very key, because it's all about a matter of perspective. In physics, this equation looks like this. That's why do not get confused. It's the same equation, but it's all a matter of what you're looking at work with, okay? So, again, the sign is going to reflect the system's point of view. In our situation, in terms of chemistry, the sign is going to reflect the system's point of view. Always take the system's point of view, POV, system's point of view, okay? So if there's a quantity of energy that flows into a system, right? If it flows into a system via heat, we're going to call that an endothermic reaction, meaning Q is going to be positive, right? Q is going to be positive, right? Where the positive sign is going to indicate that the system's energy is increasing. But if the energy flows out of the system via heat, which is an exothermic reaction, so this was endothermic, and we talk about an exothermic reaction, then that Q will be negative. That sign will change to a negative. Okay, so that's pretty simple. Now, we can apply the same conventions to the flow of work. So if the system does work on the surroundings, notice the words, if the system does work on the surroundings, meaning energy is flowing out. So system does work on the surroundings, meaning energy is flowing out, right? Then W is going to be negative. On that same token, if the system gets work done on, right? If the system gets work done on itself, or if, in other words, if the surrounding does work on the system, right? Then that W is going to be positive. So if surrounding does work on a system, then W is positive. Okay, very, very, very important to get this straight. A lot of students mess this up very often, so make sure you have a really good understanding of what's going on here. Okay, so there's a common example of the work that's done in terms of a chemical process is the work done by a gas. Okay, the work that's done by a gas. And we call them, in talking about this, is in a piston, right? And it's through compression. So if we take a look at a piston, we'll just draw a cylinder here, right? And so there's a center disk. There's some, gas here. Let's just call it gas. And then there's a pressure that's exerted on this gas. So what is that pressure, right? So if we have a gas that's confined to a cylinder, right, and this piston that's movable, then the force acting on the piston area of A, this has a surface area A, there's a force that's acting on that. That's going to equal pressure. So pressure is equal to the force acting per unit area, okay, F over A. All right, so that's what's going on here. Now, work basically is defined as the force applied over a distance, right? Work, we said, was force applied over a distance, F times D, right? So if the piston moves a distance h, right? So let's say it's going from here to, we'll change the color to, let's say it's going to here, right? It's changing a height, delta h. If the piston's going to move a distance, delta h, then that work is going to be W equals F times D, which is equal to F times delta H, right? And now since pressure equals force over area, then force is equal to pressure times area, right? And then we can substitute that into this equation, and such that work then is equal to pressure times area times delta H. So basically then, what's going on with the volume, right? We need to bring in volume in here. So if we're actually moving this at delta H, then this delta H is the movement of this plate, right? So it's not really talking about the volume. Now, this movement actually causes a change in this entire volume, right? And that volume is the shape of a cylinder. So I'm going to draw it in green to kind of highlight that. And that's the volume, the change in volume. This is delta V, right? So let's introduce that delta V in here, right? So if the volume of the cylinder is equal to the area, right, is equal to the area of the piston times the height, that's the volume, right? So then just V is equal to area times delta H, right? So then delta V is equal to A times delta H because there's a change in height, right? So then delta V is equal to final volume minus initial volume. And that equals A times delta H. Now, we're going to substitute this equation right here into our equation for work. Okay, so we're going to put that in here. Now, so what that's going to equal then, because notice this is also A times delta H. So then that's going to equal is work is equal to pressure times area times delta H, or in other words, work is equal to pressure times delta V. Okay, that this gives us that the size of the work that's required to kind of expand a gas, delta V, against a pressure P. That's the work that's required to do this. Now, what about the sign of the work? Because remember, it's always about the sign of the work that gets everyone tripped up. So again, if the gas is expanding, gas expanding, meaning the system is expanding, right? Then it's moving the piston against the pressure, meaning the system is doing work on the surroundings. Therefore, work is going to be negative. Gas expanding, system is doing work on the surroundings, which means work is going to be negative. Okay? Therefore, if a gas is expanding, delta V is a positive quantity because volume is going to be increasing, right? So it only makes sense that we make it that delta V and the W must have opposite signs, right? So we're going to say W is equal to negative P delta V. Now note that for a gas that's expanding, right, against an external pressure P, right, the work is going to be negative. It's going to be a negative quantity that's required, right? And the only reason that is because the work it flows out of the system. That's when the gas is expanding. Very, very key, because when the gas is being compressed, delta V is a negative quantity because the volume is decreasing. So compression means delta V is negative, because the volume decreases, right? Which makes W a positive quantity, meaning that the work flows into the system. So W equals positive because work flows into the system, right? And we'll basically pick up with enthalpy and calorimetry.